Okay, good morning. I have some bad news for you. This is going to be a long video. Really sorry, Miss Penner and I talked about it, and we both agreed this is just the way it has to go. We got one section left to do, and we just got to get it done. So, it's going to be a long video. Here's the next part here. You may be wondering why it is that we are looking at some ketchup on paper. The reason we're looking at ketchup on paper is because I didn't have any paint, so I just used some ketchup. So last time I gave a lesson on finding inverses by graphing. It didn't go all that well, at least for one class. And, well, anyway, the graphing went well for one class. The algebraic part went well for the other class. I'm not really sure how that happened, but whatever. Here it is. So here's what we need to know. When we are, and you can see the xy, if I flatten this down here, the light will help us out here a little bit. So we can see here that we have the y-axis and we have the x-axis. And then we have this dotted line here. You can kind of see it. It's in blue. And I put a fold on it. We have the line y equals x. And we recall from the lesson before that what we need to do is we need to reflect our function, given by the ketchup here, over the line y equals x. Some of you were reflecting over the x-axis, some of you were reflecting over the y-axis, and some of you were, I have no idea what you were doing. So we're going to reflect over the y-axis. So here's how we're going to do this. So what we're going to imagine here is that we have this ketchup here, this paint, this function, whatever, and we're just going to reflect it over this line here. Well, here's the easy way for us to do this. I'm just going to fold the paper and bring it down to the ketchup, and then I'm going to unfold it, and then we're going to see the inverse function over here. So here goes. So I'm going to fold the paper, not too far. I don't want to fold it too much, just enough. So you got some ketchup on the other side there. And then we open it up. Go. Yeah, there we go. That works. Okay. So now we can see that the original function is over here. And then we reflect it over the line y equals x, and we get this function over here. And we can see that the closer this function is to the line y equals x, the closer the inverse is to the line y equals x. The further away it is from the line y equals x, we reflect right through the line, right out the other side, and we get the function over there. Same thing here. We got this endpoint. We reflect right through the line, right out the other side, and there it is. There's where the inverse is. So there is my ketchup demonstration. Hopefully you will remember that forever, how to form an inverse function using ketchup. Okay, that goes on the ground. Back we go to the lesson here. So, like I said, this is going to be a long lesson, but I'll go as quickly as I can. If you need to pause the video while you're taking notes and stuff, pause the video. Okay, so with the ketchup in mind here, so here we have some ink, which is going to represent our ketchup, our function, and we remember that we're going to reflect over the line y equals x. That's the line that goes diagonally right through here, y equals x. That means every x is the same as every y. So we got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, negative 1, negative 1, negative 2, and so on. It's a 45-degree angle. What we want to do is we want to reflect this guy across this line right here. So just the same way as the ketchup did. So we're going to get the same kind of thing here. So actually I'm going to go in green. So here we are, this point right here, and I want to reflect this point right through, right out the other side, exactly the same distance, or at least pretty close to the same distance. Kind of eyeballing it here. And we'll take another key point right here, and we'll reflect that one straight through, just like the ketchup. We're going to go out the other side, and there we are right there. And we got another key point right here. We're going to reflect that right through, right out the other side, and there we are with that one. And then we got lastly this one, and we're going to reflect right through, out the other side, and we're there. And then we connect our dots. And we can see that this is the reflection of this over the line y equals x. Again, as though this were ketchup, and we folded this over, got the ketchup on the paper, and folded it back, and there it is. Somehow it turned green. I don't know how that happened. All right, here we are. Same kind of situation. We have the ketchup on the paper, and we have the line y equals x, and you have to reflect this over the line y equals x. So it's going to be the exact same show as we just did. We'll make it in green. So here we have our point. We want to go straight through to the other side, and we have that point right there. This point here is really close to the line, so its reflected point is also going to be really close to the line, just on the other side. Let's pick this guy right here, and we'll go straight through out the other side. Hopefully I did a good distancing there. Now this point's really easy to reflect because it's right on the line, so I don't need to reflect it anywhere. It stays exactly where it is. And this point here, I'm going to reflect through to the other side, and it'll go right here. So now I'm just going to connect the green dots, and I have my inverse function. So just reflected over the line, y equals x. So it's just a little quick review from the last lesson. Okay, then we have finding inverses algebraically. So what we learned from that was that we need to first rewrite this with y equals x plus 1 squared. And again, this is review. We did this before for the 7 of you that did your homework assignment. And then once we have it written this way, we just switch the x and the y. Plus 1 squared plus 3. And then we solve for y. And we should remember that when we're solving, we do reverse PEMDAS. So we do SADMAP. So we do all the add subtract pieces first, then the multiply divides, then the exponents, and so on. So we're doing SADMAP, so we're going to take care of all the add subtract pieces first. So we're going to subtract 3 from both sides. So we get x minus 3 equals y plus 1 squared. Okay, now we're on to multiply and divide. There isn't any of that. We have an exponent. We need to move that exponent over. So we're going to take the square root of both sides, whoosh, right over to there. So now we have the square root of x minus 3 equals y plus 1. And of course, since we square root both sides, we got to do plus and minus. And then we're going to have to subtract 1. So we're going to subtract 1 right over to here, and I'm just going to rewrite this in an order that makes more sense. So I'm going to write this as y equals plus or minus root of x minus 3 minus 1. Right? Close that off right there, and the minus 1's on the outside, so subtracting 1 over there. So again, write it in terms of y, switch the x and the y, solve for y using SADMAP. Again, I'm going fast, so if you need to go back and replay it, pause it, whatever, do that. Okay, same kind of show right here. We got f of x equals, so we're going to turn this into y equals root of 3x minus 4. And then we need to switch the x and the y, so we get x equals root of 3y minus 4. Again, if you got to pause, please do. Now we're trying to get the y out of there, so we need to square both sides to get rid of the square root. So we get x squared equals 3y minus 4. And now we're back to SADMAP. So we do all the add subtract pieces first. So we're going to add 4 to both sides. So we get x squared plus 4 equals 3y. Then we're going to divide both sides by 3 and flip it around so we have a more orderly sense here. So we get y equals x squared plus 4 over 3. Oh, yes, we need to write in proper format here. So I'm going to write that right up here. So f inverse of x. Instead of y, we're going to write f inverse x squared plus 4 over 3. I should have written that for the last one. But as you know, I'm trying to hurry here along so this video doesn't take forever. Okay, so on to simplifying numerical roots, square roots, by the way, and cube roots. There are lots of other roots, by the way, but we're just going to simplify square roots and cube roots. In order to simplify square roots and cube roots, we need to know the list of perfect squares and the list of perfect cubes. There are obviously way more than these, but up to 64 will be fine for our purposes today. So if you forget these, that's fine. You can always remake them yourself. So the list of perfect squares, you just do 2 times 2 makes 4, 3 times 3 makes 9, 4 times 4 makes 16, and so on. Same thing over here with the cubes, only got to do it 3 times. So 2 times 2 times 2, well, that makes 8. And 3 times 3 times 3, that makes 27. 4 times 4 times 4, that makes 64. So this is how to generate your perfect cubes, cube squares. Okay, so we want to simplify. So, and again, theoretically you've done this before, but I always find that Most of you have kind of forgotten a little bit. So when we're going to simplify the square root of 45, we're looking for the biggest one of these that goes evenly into that. And so we're looking here, and we see that 9 is the largest one that goes into there. So we're going to rewrite this as the square root of 9 times 5. And which one of those two numbers is square rootable? Well, obviously the 9 is, so this is 3 root 5. And that's the answer to that. And then we have the square root of 96. So again, we're looking for the largest perfect square that goes evenly into this. And the largest one that goes evenly in is 16. So we're going to have the square root of 16 times 6. Which one of those is square rootable? The 16, obviously. So we root it. So that's 4 root 6, and we're done. Let's jump over to the cubes, the cube roots, I should say. So we're looking for the largest cube root, or cube, that goes into 40 evenly. So 8 fits the bill right there. So we're going to have, this is the same as the cube root of 8 times 5. And of course we know that this number is the one that's cube rootable, and the cube root of 8 is 2. We're still taking a cube root here, not changing it to square root. And 5 is what didn't get cube rooted. Same trick down here with a little more space. So cube root of 108, we're looking for the largest one of these guys that goes into that. And it turns out that it's going to be 27, because 27 times 4 is 108. So we got that, 27 times 4. So the cube root of 27 is 3 times the cube root of whatever we didn't cube root, which is 4. So there we have now the cube root of 108. 3 cube roots of 4. Okay, our first page is done, plus the review. All right, that's not too bad. We are 12 minutes in. Well, I'm going to try to keep this under half an hour. All right, simplifying roots of variable expressions. Here's the rule. It's really simple. Divide the power by the root, also known as the index. So you can see here, this is a cube root, so the index here is 3. Cube root here, the index is 3. This is a square root, and when we say x squared, what we really mean is that there's a 2 there. So we don't generally write the 2, but there's a 2 right there for a square root, right? Just like when we write x squared, there's a 2. A square root has a 2. All right, so the rule is divide the power by the root, or the index. So the index here is 2, so 8 divided by 2 is 4. Simple. X to the 4th power. Even a caveman could do it. All right, and then we do the same thing. So again, it's a square root, so the index is 2. So we get x to the 10th, so 10 divided by 2 is 5. X to the 5th. Y to the, I can't even see that, 16th. Y to the 16th. So 16 divided by 2 is 8. Y to the 8th. We're going to come back to this in a little while. I'm going to make believe I didn't see that, and you don't need to see it either. You can just make believe with me. Okay, so we're going to do now the cube root of x to the 18th. So again, the rule is just the same. Power divided by index. 18 divided by 3 is 6. So we got x to the 6th. Easy. Same trick down here. Just divide everybody by 3. Could be 4, 5, or 6, or 10, or 100. So 33 divided by 3 is 11. So x to the 11th. Easy. Y to the 21st divided by 3. 21 divided by 3 is 7. Easy. Easy stuff here. So, well, what happens, you might ask, if the index does not divide in evenly? Well, I have an answer. Just put the leftovers in the root. So, let's find out what we're doing here. So we're going to do, just as we did up here, the rule is still divide the power by the index. So we got 13 divided by 2. So I'm just going to do that work right over here so we can kind of see what's going on for the first one of these. So we're going to divide 2 into 13. Well, how many times does 2 go into 13? 6 times. 6 times 2 is 12. And we have 1 left over. So I'm going to show you how this, particularly these two numbers here, work into this. So the answer for this guy here is going to be x to the 6th, right? Just like we did before. We divided, and we got an answer right here. So this is when we divide. So 13 divided by 2 is 6, and we have 1 left over. Well, what did I say? Just put the leftovers inside the root. Well, it is a square root, so we keep it as a square root. And we have a leftover. We have 1 left over. We have 1x left over, x to the 1. That 1 is right here. The remainder is right here. The power is right here, x to the 6th, right? X to the 6th, root x to the 1st. If this was a 2 or a 3 or a 4, we'd have a 2 or a 3 or a 4 right here. But of course that wouldn't happen because we're dividing by 2. So here is your answer. It's just the same. 13 divided by 2 is 6 with 1 left over. Going to do the same thing down here. Only this time we have a cube root. It's just the same. So we're not going to do the long division thing here because you can do this in your head along with me. So 17 divided by 3, of course, is 5. So we got y to the 5th. And then is there anything left over? Remember, if there's anything left over, we put it inside the root. So 17 divided by 3 is 5 with 2 left over. Right? 17 divided by 3, 5, because 5 times 3 is 15. How many more do we need to make 17? 2 more to make 17. 2 is the remainder. All right? And we're doing remainders in our head here. And then we got 34 divided by 3. Well, 34 divided by 3 is 11, because that makes 33. And we have 1 left over. And we're not even going to write the z to the 1st. We're just going to write z because we all know that that really means z to the 1st. All right. So that is what we do when we have some leftovers, when it doesn't go in evenly. There are other problems, of course. So there is a weird rule involving odd results. So if the result is odd, then we got this weird thing going on and we need to check it out. So here's the rule. If dividing by an even index, not any index, got to be even, 2, 4, 6, 8, and so on, an even index, and the result, or that results in an odd power, use the absolute value. So I'm just going to give you a little quick explanation of that. You don't need to really know it all that much, but here it is. This thing right here means the positive root. So when we simplify this, it must be a positive number because this square root thing here means positive root. When we have plus, that means positive root. If we have plus and minus, that means the positive root and the negative root. But we don't have any minuses here. These are all positive roots, so the result has to be positive. So let me give you a hypothetical here. Let's just say for kicks that after we square rooted something, actually we'll do that. Actually, we'll get rid of this. And we'll do it right over here. So what's going to happen here is we're going to divide like we did before. So 10 divided by 2, this is a square root still. So we're going to do 10 divided by 2. So we got x to the 5th. Now let's just say, just for the moment, that x happened to be, in this problem, -1. So -1 to the 5th power, well, -1 to the 5th power means -1 times -1 times -1 times -1 times -1, 5 times. And so when we multiply all those negative ones out, it turns out that that will be negative. And we just discussed that this root here has to be positive. So if x happened to be -1, then -1 to the 5th power would be negative, and that's not okay. So what we do is we put absolute value on here to force it to be positive. So the rule is still the same. Still divide, but if we have an even root and we end up with an odd result, we have to use absolute value every time. So here we go. X to the 44. So 44 divided by 4 is 11. That's an odd number. So x to the 11th goes inside the absolute value. Got to happen. So 36 divided by 4 is 9. 9 is odd. Y to the 9th. If we wanted to, we could put those guys together and we could get this. X to the 11th, y to the 9th in absolute value. Also good. All right, same trick here. Only again, now we have two things going on. We have not going in evenly, then we have odd stuff going on. Okay, so 15 divided by 2 is 7. And there's 1 left over. and 20 divided by 2 is 10, with none left over. Now we just need to check here. Is this an odd result? Yes, it is. It gets absolute value. Is that an odd result? No, it's not. It doesn't need the absolute value because if this was -1 to the 10th power, that would still end up being positive. So here's our result right here. So the rule again is if when you're taking this square root or the fourth root or any other even root and you end up with an odd powered answer, you must put that in absolute value. Okay, now we're just going to combine the numbers and the variables. So everything that we did with the numbers, still true. Everything that we did the variables, still true. We're just going to do it at the same time now. Okay, so we're looking at 32 here, and so we're going to find the largest perfect square that goes into 32. That turns out to be 16. So we're going to rewrite this, and I'm going to do 16 times 2 times x to the 12th times y to the 7th, right? Just rewriting the problem with some multiplication signs just to kind of clear it up a little bit. Okay, now we're just going to go through and we're going to start square rooting everything we can square root. So can we square root 16? Yes, we can. It's 4. Done. Can we square root 2? Well, not very well. So we're going to put that in the root. Leave it in the root. We didn't do anything with it. We didn't square root it. We just left it because we couldn't. So that one's done. X to the 12th. So the square root of x to the 12th, same rule as we just did. 12 divided by 2 is 6. Is there anything left over? No. Is this odd? No. Good, we leave it. Done. 7 divided by 2 is 3 with 1 left over. Is 3 odd? Yes, it is. Therefore, it needs absolute value. And we're done with that one. Sorry I'm going so quick today, but again, this will be like a 45-minute video if I don't go fast. Again, you can pause and go back as much as you need. So again, we're going to do the same trick right here. We're looking for the largest perfect square that goes into 80. Turns out that that is 16 times 5 times x to the 11th times y to the 23rd. All right, and then we just go through, we root everything we can root. So the square root of 16, you guessed it, 4. Done. Square root of 5, not so much. Done. 11 divided by 2 is 5 with 1 left over. Of course, we don't write the 1. Done. Oh, actually, is x to the 5th, is that an odd power? Yeah, it is. Absolute value. 23 divided by 2. 23 divided by 2 is 11. Y to the 11th with 1 left over. It is also odd. And again, we could combine those two absolute value things together, but time and space. Do we do both sides? Nice. Good. All right. Moving right along here. We're at 23 minutes. All right. Trying to keep this under half an hour, but yeah, it's going to be rough. All right. So here we are. Cube root. So the cube root is the same as the square root, only we need to use the largest perfect cubes that go into this. So the largest perfect cube that goes into 56 is 8. If you got to go back and check the list that you wrote in your notes, then please do that. And of course, we all know that 8 times 7 is 56. And we have y to the 16th. Okay, now we just start cube rooting stuff as we go. Oops, that's a cube root. So the cube root of 8, yeah, that's 2. Cube root of 7, nope. That can't be done very well, so we just leave it. X to the 12th, so 12 divided by 3 is 4. X to the 4th. 16 divided by 3, well, 16 divided by 3 is 5. That's y to the 5th. And there's 1 left over. Y to the 1st. We don't write the 1. Okay, now let's take a look at this guy here. This is odd, and you think, well, that's got to get absolute value. But remember the rule. If we have an even root that ends up in an odd-powered result, then we use absolute value. This ain't even. We don't need absolute value. Because, as we know, the cube root of -8 is -2, and that's perfectly fine. There's nothing wrong with -2 for a cube root. So this is the answer. Okay, so we're going to add and subtract roots. So the rule is only like roots can be added or subtracted, just like fractions. So what we need to do here is we need to simplify each of these. Well, actually, first of all, let's see if we can add these guys as they are. 5 root 12, 2 root 27, minus root 128. These are not the same roots. They're not like terms. We can't add or subtract them. But maybe after we simplify them, maybe we can. So let's see if we can find a perfect square that goes into 12. And yes, we can. It's 4. So we got 4 times 3 plus 2 root largest perfect square that goes into 27. You guessed it, 9 minus square root of 128. Largest perfect square that goes into that is 2. 64 times 2. So now we square root the 4, which of course is 2. And this is 5 times that, so 2 times 5 is 10. So we got 10 root 3 plus square root of 9 is 3 times the 2, right? This is 2 times. So 2 times 3, square root of 9 is 3. 2 times 3 is 6 root 3. And square root of 64 is 8. So minus 8 root 2. Any of these terms like terms now? Yeah, these two guys are. 10 root 3s plus 6 root 3s make 16 root 3s minus 8 root 2s. The root 3s and the root 2s don't go together, or they ain't the same. So there we are. We're done with that one. Same kind of problem right here. We're just going to find the largest perfect square that goes into this one, and this one, and this one, and simplify. And you know something? I'm just going to save some time and not do that problem. So here we are. We're going to jump down here. We're going to multiply by FOIL. We have multiplied by FOIL a bajillion times. So it's the same thing whether we got roots or not. I just want to point out one thing. I'm going to use this space right here to point out one thing. So if we have the square root of 3 times the square root of 3, well, root 3 times root 3 logically makes square root of 9, right? Because 3 times 3 is 9. Well, the square root of 9 is just 3. So what happens when you multiply root 3 times root 3? You just get 3. If this was root 5 times root 5, you'd get 5. Root a million times root a million, you get a million. Root a billion times root a billion, you get a billion. You get the idea. So we're going to apply the same trick right here. So multiplying by FOIL. So 3 times 6, that's 18. Easy enough. And then 3 times this last thing here, 3 times 4 root 5 is 12 root 5. No problem. And then we got multiply by 6. So 6 times 2 root 5 is 12 root 5. And then we're going to multiply the last ones here, keeping in mind this little trick right here. So we're going to multiply 2 times 4, that's 8. That's easy enough. So we got negative 8. I'm going to keep that up here in my brain, negative 8. And then I got root 5 times root 5. Well, I know that root 5 times root 5 is 5. Same trick up here, right? Root 5 times root 5 is 5 times 2 times negative 4, that's negative 8. So 5 times negative 8 is minus 40. And then we put all the like terms together. So 18 and negative 40 together make negative 22. And then these two guys together, negative 12 root 5 plus 12 root 5 make, that's not what was supposed to happen here. Weird. Didn't expect that. All right, well, these are just going to cancel out because negative 12 root 5 plus positive 12 root 5 cancel right out. If this was like negative 10 root 5 plus 12 root 5, this would be 2 root 5. So a little bit of trickiness there. We just lost our root 5s. But you get the idea, multiplying by FOIL. Okay. Let's jump over to the other side. We get another chance to multiply by FOIL again. But this time we have roots that are not going to be the same, and there's definitely going to be no canceling out here. So FOIL again. Foiled again. So 3 times 5 is 15. And then multiply over here, 3 times negative 3 root 3, which makes negative 9 root 3. And 4 root 6 times 5 is 20 root 6. And 4 root 6 times 3 root 3 makes negative 12, right? Multiply the 4 times the 3 makes negative 12. And then root 6 times root 3 is root 18. Now hopefully you're looking at root 18 going, I recognize that. That is 9 times 2, because 9 is a perfect square, then goes right into that. So we're going to have the whole show again. 15 minus 9 root 3 plus 20 root 6 minus, so this is going to be 12 root 9 times 2. So the square root of 9, of course, is 3, times 12 is 36. So we got 15 minus 9 root 3 plus 20 root 6. And then again, 3 times 12 is 36, minus 36 root 2. Any like terms here? Nope, root 3, root 6, root 2. None of those guys are like terms. So this is the answer, as messy as that is. Okay. Multiplying radicals with variables. So, not terribly different than you would imagine. So we're just going to multiply the numbers on the outsides. So 6 times 5 is 30. That's easy enough. And we're going to multiply all the stuff on the insides using the rules that we already know. So 3 times 7 is 81. That's easy. And when we multiply things with exponents, we add the exponents. So x to the 7th times x to the 4th is x to the 11th. And then we need to simplify. So, is 81 a perfect square? It is. In fact, 9 is the square root of 81. So we're going to do 9 times 30 makes 270. 270 root x to the 11th. Well, now we're down to taking the square root of a variable to a power. We know how to do that now. We divide 11 by 2, and we're going to get 5 and 1 left over. So we're going to get 270 x to the 5th root 1 left over. Now we go back to look at this and we go, oh yeah, that's an odd powered answer. It's an odd answer from an even root. Absolute value right there. And again, I know I'm going fast, and I'm sorry. We just need to get this stuff done. And Miss Pender and I decided that this was the only way to do it. Just get it done in one lesson. So if you need to pause and go back, please pause and go back. And I apologize for going as quickly as I'm going. Okay, so we're doing square roots again. So it's the same trick. So we're going to multiply the numbers on the outside. 4 times 7, that's 28. Multiply the stuff on the inside, so we can make one big root out of this, so we can simplify it. So 6 times 15 is 90. And then x to the 8th times x to the 2nd is x to the 10th. And y to the 9th times y to the 2nd is y to the 11th. Hopefully I don't want to run out of room here. So obviously the largest perfect square that goes in a 90 is 9. So we're going to have 28 root 9 times 10 x to the 10th, y to the 11th. I'm going to finish that up over here. So the square root of 9, of course, is 3 times 28 is 84. Boy, I sure hope all this fits. And so we took care of that. Square root of 10, not so much. Yeah, this isn't going to fit. Damn it. So we got square root of 10, so that's right there. So x to the 10th, square root of that. So we do 10 divided by 2, because that's the index right there, right? 10 divided by 2 is x to the 5th. And we know the tricks by now, because that gets to be an absolute value. And that's done. And then y to the 11th. 11 divided by 2 is 5. Y to the 5th. Crap, there's not enough room in there. With 1 left over. And this gets an absolute value, and I have no idea I'm going to draw an absolute value in there. That's the best I can do. Okay, so this was a little short on space there, but it worked out okay. So again, multiply the numbers on the outside, multiply the numbers on the inside, add all the exponents together, so we get this, and then we simplify this guy here using all the rules we just had. Okay, cube roots, same rules. So we're going to multiply the numbers on the outside. 2 times 9, she is 18. Then we got the big cube root here. 4 times 6 is 24. X to the 7th, x to the 3rd, x to the 10th, and then y to the 4th, y to the 5th, y to the 9th. And then we look for the largest perfect cube that goes into 24, and of course that is going to be 8. So we got the cube root of 8 times 3 times x to the 10th times y to the 9th. And we just go across. So we got 18 And actually, I'm not going to write 18. Save myself some time. So the cube root of 8 is 2 times the 18 makes 36. So that's done. Cube root of 3, not so much. Put that right over here. Cube root of 3. We're done with dealing with that. 10 divided by 3. Well, 10 divided by 3 is 3 with 1 left over, right? Because 3 times 3 is 9. I need 1 more to make 10. And then we got y to the 9th divided by 3 is y to the 3rd. So you're thinking, hey, I need to put absolute value around these two guys, but you know, we don't, because we're taking a cube root, which is an odd root. That rule only applies when we're working with even roots. So no absolute values there. Okay, done with that. All right, I did that page. Awesome. All right, making good progress here. 35 minutes. Yeah, this is not good. Really sorry. All right. Okay, so rationalize the denominators. So we are going to rationalize the denominator, which means to make it into a rational number. So the square root of 6 is not a rational number. If we try to take the square root of 6, we would not get a terminating decimal. We would not get a repeating decimal. We'd get this decimal that goes on and on forever with no repeating. So this is an irrational number. So the way to address that is we want to get it into a rational number, because you know, you guys don't like working with fractions, even with nice numbers in the denominator, much less horrible numbers like the square root of 6 in the denominator. So, no, the square root of 6 is horrible. I like the square root of 6. So what we need to do here is we need to rationalize this, and the way we're going to do that is we're going to first simplify whatever we can simplify. Nothing to be simplified here. Then we're going to multiply the numerator and the denominator by a radical that turns the denominator into something rootable. Okay, so what we need to do is we need to figure out what is it that we can multiply root 6 by so that it becomes the square root of something that's easy to take the square root of. Well, in this case, really the easiest thing to do is just multiply it by itself, because we all know from that experience that we had just a few minutes ago that when we multiply root 6 times root 6, we get root 36, which of course is just 6. So in many cases, rationalizing the denominator really just means multiplying the denominator by exactly what's there. So 2 times root 6 is 2 root 6. And root 6 times root 6 is 6. But of course, we would never leave 2 over 6. That would be just horrible. We need to make that into a 1/3. So we got root 6 over 3. So what we're trying to do here is we're trying to rationalize the denominator, which means turn this irrational number into a rational number. 6 is a nice rational number, by multiplying it by essentially by itself. So that's what we did. We're multiplying root 6 over root 6 to clear that denominator and get into a nice rational number. Okay, so second example looks very similar to the first one. However, we got a root in the top. I just wanted to make it a little more complicated. And we got a root in the bottom that is simplifiable. And it says here step 1 is to simplify. So we're going to simplify first. So we're going to have a root of 3 because that's not simplifiable. And then this is going to be the square root of 4 times 2. And that, of course, the square root of 4 is 2. So now we got root of 3 over 2 root 2. Well, the only problem number here is this guy right here, the square root of 2, because that's irrational. 2 is nice. It's a nice rational number, but root 2, not so much. So we need to multiply the root of 2 by something so that we can square root it easily. And again, the whole trick that we had here before, multiplying it by itself is pretty much going to be the way to go. So we're going to multiply by root 2 here. And as always, whatever we do to the denominator, we got to do to the numerator also. Then we just multiply straight across. Root 3 times root 2 is root 6. And root 2 times root 2, well, we already know the trick here. Root 2 times root 2 is root 4, which is just 2, right? Root a million times root a million is a million. So root 2 times root 2 is 2. Times this 2 makes 4. So we got a 4 there. That's a nice rational number. This is done. Okay, so here we get a little bit trickier. So when we have a cube root in the denominator, what we want to do is we want to multiply by something so that when we try to take the cube root of it, we can. So what's an easy number to take the cube root of? Let me think here for a really long time. 8. 8 is an easy number to take the cube root of. So, because we all know the cube root of 8 is just 2. So what is it we can multiply 4 by so that it becomes 8? Well, that's easy. 2. So we're going to multiply top and bottom, by cube root of 2. Now I know that's different than what we just did, but this is a cube root and not a square root. So we're going to multiply by the cube root of 2. So multiplying straight across the top, we get 5 cube roots of 2. And straight across the bottom, cube root of 4 times the cube root of 2 is the cube root of 8. And of course the cube root of 8 is just 2. So we get 5 cube roots of 2 over 2. And that's all I have to say about that. Okay, so the next example here involves a variable. And we're back to square roots. So we're just going to approach it the same way we did up here. We're just going to multiply the denominator. Well, first simplify. This is already, well, actually the top isn't simplified. We'll simplify the top first. So the square root of x to the fourth is x squared over root 3y. And since this is already simplified, we use the rule up here that we did. We multiply the denominator by itself, and that will make it into a rational number. So we're going to multiply by root 3y, and so we have x squared, root 3y, and root 3y times root 3y is, well, you guessed it, 3y. Hopefully you're watching this in segments because this is a long video, and I'm really sorry it's a long video. Okay, so rationalizing a binomial, rationalizing when we have a binomial denominator. So we're going to multiply by the conjugate. So instead of just multiplying by the square root of 6, like we did up here, that won't help because we multiply the square root of 6 here. That makes that into a nice number, but that turns into 3 root 6, and that's not okay. So what we're going to do is we're going to multiply by the conjugate, which is just this binomial here with the sign in the middle changed. And when we change the sign in the middle, that means that some things are going to cancel off. So we've got 3 minus root 6. So this is called the conjugate right here, right? This guy here, these two are the conjugate. So we're just going to multiply by the conjugate, which is exactly the same thing here, just change the sign in the middle. And then we're going to multiply on the top by the distributive property, and on the bottom using FOIL. This video is going to take forever to upload, by the way. So 5 times 3 is 15, and then 5 times root 6 is negative 5 root 6. And then we're going to multiply this by FOIL down here. So we got 3 times 3 is 9. And 3 times negative root 6 is negative 3 root 6. And 3 times root 6 is plus 3 root 6. And positive root 6 times negative root 6. Well, again, of course, we all know that root 6 times root 6 is just 6. And a positive times a negative is a negative, so we got minus 6. And barely we have enough room. So here on the top we have 15 minus 5 root 6. And in the denominator, watch the magic here. We got negative 3 root 6. We got positive 3 root 6. Those guys cancel right off. And we got 9 subtract 6 is 3. And if we could simplify this, we would, but we can't, so we won't. And that is that. And holy mother of God, we have more to do. All right, so here we go. So here we have the same kind of situation here where we have to multiply by the conjugate. So we will get right onto that, multiplying by the conjugate. So we're going to multiply by 2 plus root 10. Again, everything stays exactly the same except for the sign in the middle. 2 plus root 10. And we're going to multiply the top as it is and multiply the bottom by FOIL. So root 3 times 2 is 2 root 3. And root 3 times root 10 is root 30. Easy enough. And on the bottom, it's going to be the same show as we just did. So 2 times 2, she is 4. 2 times positive root 10 is 2 root 10. 2 times negative root 10 is negative 2 root 10. Those guys cancel off just as we predicted. And negative root 10 times positive root 10, remember root 10 times root 10 is just 10. And a positive times a negative is a negative, so that's going to be minus 10. And then 4 minus 10 is negative 6. And this is the same on the top. We don't change anything up there. And we are done with that. I'm not going to do that because this is getting ridiculous. We need to move along here. All right, so finding roots of fractions, 3 easy steps, and most of which we've already done. So first is split the fraction, second is to simplify, third is to rationalize. So we're going to split the fraction. So we got root of 6x, root of 5y to the 5th. All right, so root of 6x can't be simplified, so we just leave it. And we got y to the 5th can be simplified because we're taking the square root of y to the 5th. So 5 divided by 2 is 2 with 1 left over. And then we need to rationalize this guy right here. We have a square root in the denominator, trying to get rid of it. So we're going to multiply by the square root itself. Root 5y, root 5y, and root 6x times root 5y, just multiply the numbers, that's 30, and multiply the variables, x times y, well, that's just xy. And then we multiply this stuff on the in the denominator, so we still got y squared times the outside here, which is 1, so that's just going to be y squared. And then root 5y times root 5y is, you guessed it, 5y. And then we're almost done. So on the top we got root 30xy, and on the bottom we have 5y cubed. And that is all I have to say about that for that problem. And we are almost done, I promise. We have one more side left, and this is really easy. Okay, rational exponents, aka fractions. We got fractions as our exponents. We're used to having like x squared or x cubed or something like that. Now these guys are going to become fractions. So, and it's easy to deal with. The thing that we're raising to a power is always known as the base. The top of the fractional piece here is the power, and the bottom is the root. And you can remember that by the trees. The roots are in the bottom, just like in the trees. Roots are in the bottom, and the power comes in the leaves. They're on the top of the tree. So power on the top, root on the bottom. Base is always, well, the base. Okay, so we want to rewrite the expression in radical form. So remember, the top is the power, the bottom is the root. So we will write first the power, 10 to the first. We don't really need to write it, but for instructional purposes I'm going to. And then the bottom is the root. So we write this as a root. 5th root. Done. Root out there, power in there. Same thing right here. So we got AB, that's what we're going to be working with. I'll put it in parentheses just to keep it clean and simple. And then we have the power, which is 3. That's on the top, and the root is on the bottom. So we write the root. And we're all done with that anyway. Now we're going to do the exact same thing, only we're actually going to simplify. We got 2 more problems to go. We're almost done. Okay, so first thing we're going to do is we're going to write it in radical form, and then we're going to simplify it. So we know that we got 8 to the 2nd power. I'm going to do this, and you're going to see a little bit of trickery here. I'm going to put that 2 way up there because we're going to use it later. And then we have the bottom number is the root. So we're going to write the root right here. And the reason we're doing it this way is because when we take the cube root or the rooting first, we get smaller numbers. Then we can take a power of a smaller number rather than the root of a bigger number. So we're going to root first, then power. I think I'll write that down. So root first, then power. When I sign this, I'm going to suggest that you write it, or that you view this in 2 parts. So let's do the cube root of 8, which of course we know is 2, and 2 squared is 4, and we are done with that. Okay, 2 more examples. All right, same trick right here. So we got the number, we got the power, and this is a square root, right? Bottom number is 2, so it's a square root. So then we just simplify. Square root of 25 is just 5, and 5 to the 3rd power is 125. Okay, and last little bit right here. Combining a few things from back in the day. So anytime we have something to a negative power, that means 1 over that thing to the positive power. Oh, I need to run over something here in just a minute. So then we have here 81 to the first power, which of course is just going to be 81. So we got 81 to the first power, and then we got fourth root. Fourth root of 81 is 3. And 3 to the first power is just 3, so this is 1/3. And we're done with that. Okay, so I do want to emphasize this a little bit right here. 1/2 power equals square root. 1/3 power equals cube root. Very important. Okay, there it is. There's your video. Sorry it was so ridiculously long, but that's unfortunately the way it is. So I will see you all on, I don't know, today's Monday, right? Wednesday. See you on Wednesday. Be safe.